Howdy, Brian Vikings. We're here to start our solids and liquids unit. This will immediately follow gases, and we're going to start on February 27th. That's a Wednesday, and we're going to end on March 7th with our test. This is a Thursday, the Thursday before spring break. So, warming up, let's think about our kinetic molecular theory of gases. How would you modify these statements for a liquid or a solid? The kinetic molecular theory is those of gases was with those five different parts that we had to assume. So go ahead and look those up and think about that. So the kinetic theory of liquids is a model that accounts for the observed properties and behavior of liquids. And a liquid is officially defined as a matter that has flow, definite volume, but no definite shape. Here you have a solid and a liquid and a gas. The liquids are going to look like this in a comparative sense. Now there are two different parts of the kinetic theory for that. Liquids are composed of large numbers of closely packed atoms, and these atoms are more ordered than gases. So more ordered is a phrase that will start to come up and is going to be a big one starting in May. So it's okay to start to understand what the word ordered is. Yes, they're more ordered, which means they're more closely packed together. For number two, liquids are in constant motion. However, the motion is restricted due to intermolecular forces. These forces are strong enough to allow the molecules to cling together, but weak enough to allow the liquid to flow. The liquid state is the intermediate between the solid and gaseous state. So there's several different properties of liquids. They have a definite volume, have fluidity, or a fluid, which is a substance that can flow and conform to the outside of its container. Remember that gases are fluids too, okay? They filled their containers as well. They have a relatively high density. They're relatively incompressible. That's a big one a lot of people don't know. The fluids or liquids are incompressible. They have a dissolving ability and they have the ability to diffuse, so they will still spread out amongst other liquids. And they have some surface tension, and we'll get into what surface tension means later. This is what a simulation of liquids will look like when they're in motion. Now, the lines that are in between them, let me pause it for a sec. These dotted lines represent the attractions between the forces. We hadn't talked about that yet, but those molecules are attracting to each other. And you notice how they're just moving around all willy-nilly. If I mark two different atoms, you can tell that eventually they just kind of, by random cause, they end up making it to some other part and they end up filling their container. They're always in constant motion, but they're always very, very, very close to each other. So now let's move on to a kinetic theory of solids, which is a model that accounts for the observed properties and behaviors of solids. A solid is defined as a matter that has no flow, definite volume, and a definite shape. So a particle view of a two-dimensional view would look like this, and a three-dimensional view would look like this one right here. Now, solids are composed of tightly packed atoms, ions, or molecules. Solids are more ordered than both liquids and gases. So order is, solids are the most ordered and gases are the most disordered. So disorder is going to be a big word that's going to come up later too. So make sure that you're kind of sticking that one in the back of your mind. Particles in a solid are in constant motion but are unable to move from point A to point B. They have strong intermolecular forces, allow solids to only vibrate in place and rotate around a fixed point. There are several different properties of solids. They have definite shape, they have definite volume, they're non-fluid, which means they don't take the shapes of their container. They have a very high density. They're incompressible. They have a slow rate of diffusion, so they won't spread out and randomly join with other solids or other liquids. So I want y'all to fill out this comparison chart here on your for your homework. So just a preview for that. That's going to be due on the next day, which is going to be Thursday. This simulation will show you how solids look in a particle view. Let's go ahead and mark two atoms right away and turn it on, see what happens. Yeah, they just kind of vibrate, right? They don't move from point A to point B. Those molecules aren't really interchanging places or really vibrating too much. They don't have enough kinetic energy, and they're kind of locked together. That's what a solid is. So now let's move to page 3 of our notes. We're going to follow a few different parts of solids. Now, a solid can be an amorphous solid, which is a solid that lacks a definite internal structure, and the particles in an amorphous solid are randomly arranged. So, like glass, rubber, or plastic, they're kind of vibrating around. They're not moving randomly around, but there's no particular specific order to them. Now, a crystalline solid is a solid that has a definite repeating pattern of particles. A crystal lattice is a three-dimensional array of the particles that make up the crystal. The smallest part of the crystal lattice that still has the same geometric shape as the entire crystal is called a unit cell. So a unit cell is the smallest part. And you're going to want to remember this part right here, this vocab word. So here's a couple of you have pictures of these in your notes. These are some of the crystals where an ionic crystal is made of ions that are positive and negative, and they're typically very hard and brittle because if you knock down, so if you look at this is a chlorine atom, this is a chlorine atom, this is a chlorine atom, this is a chlorine atom. So if you look at this little square right here, and all the ones that are in between them. If you actually knock these down one molecule, they would be next to two negatives would be close to each other, so they would end up breaking, and that's what makes them brittle. They do have very high melting points because it's hard to break these bonds, and they don't really conduct metals. So they're usually with a metal and a nonmetal and ionic crystal. A covalent network is something almost like graphite or diamonds, is where they're covalent bonds, but they are networked in just quite a repeating pattern like this. So they're single atoms bound together. They also still have high melting points as well. And a metallic crystal is something like we've gone over before, a metallic bond, where you have the electron C that's flowing on here. And we have lots of different electrons flowing around. They're all the same repeating, well, mostly the same repeating elements that are right here. If they're not repeating elements, then that's what we would call an alloy. But that's what a metallic bond is. And a covalent molecular bond is exactly what we've studied in first semester, is just this bond that's in between this part and this part. And we'll get into that little network of how they are as well. Now, these do have lower melting points, tend to do that. And they're held together by intermolecular forces, and we're going to talk about that a little bit in a minute. This is a really cool simulation about solid crystals. Note that there are a couple of things I'm going to click on. I can have my charge, I can have my van der Waals attraction, which is the attraction between the actual molecules. And I can also talk about the temperature as well. So all of those have something to do with it. Now, if I change the van der Waals attraction, you notice that they can become more ordered and they become closer together. And now if I make them weaker, they're not attracted to each other as much, so they can move around maybe just a little bit and maybe wiggle just a little bit. So now check out what happens when I hit charge. all of a sudden it becomes very ordered, and now all of a sudden I go from neutral atoms to become a positive and negative atoms. Now, you never see a positive right next to another positive, and that is very much on a physical purpose. Let's see. So if I increase the attraction a little bit, we increase the attraction more, I become with a very more ordered solid, and I get a very crystalline structure. And this is what it would start to look like on in an actual real life simulation.